So we're doing 1.2 limits and continuity. We learned yesterday or last day about what a limit is. And so now we're going to carry on with that concept. We're going to look at it both graphically and algebraically. That's almost always going to be the case. Know that we're doing the same thing. Doing something using algebra and then using a graph is just different methods of looking at the exact same thing. That helps with your understanding. So it says a limit exists if the function connects at the region of interest. So what I am talking about here for the region of interest is, see at the bottom here, that's our A value. So if we were to, just like on any graph, I would go up to there to read off what the Y value is at that point. And since we're talking limits, I'm going to put an L there to call it L. So it says a limit exists if the function connects at the region of interest. We can tell just by looking at this first graph that it does connect there at point A. What I mean by that is if we analyze it and we look at it, the values that are approaching from the left side of the graph connect with the values that are approaching from the right side of the graph. So they are approaching the same value. That's basically what this means. And that ties in with the stuff that we did last day. So here, the limit, at the bottom here, the limit as x approaches a for f of x, so that's this function labeled here, would be equal to L. Pretty straightforward. So here, this would be, oh boy, let's fix that. This would be the x value that it's approaching, and in blue that would be what the y value is at that point. So it truly sort of is things that we've done before, we just have this new vocabulary or terminology. We're looking at it in terms of limits, but we've read things off of graphs like this before in the past, right? Okay, and then we do the same type of thing if we look at the other graph here. Where it says, but notice the difference on this graph. Notice that it says, or notice here that we have an open circle. So we learned this last year in the rational functions unit, but basically we have a hole here at the point where we have an A. But when we are looking at the definition of a limit, what it said over here is we want to check to see where the values are approaching from the left, do they approach the same value as they are approaching from the right? And although there's a hole there, the answer is yes. They are approaching or coming to the same value, which this time would also, I'm going to call it L here. So even though there isn't an actual value at our point of interest at point A, the limit still does exist. This is going to be a little bit of like nitpicky, subtle details. So I'm going slowly, I'm pointing those out to you because there's potential here to mix these things up. But we get that? So even if there's a hole there, the function doesn't exist at the point of interest at point A, but the limit does exist. So at this point, I would say yes, the limit as x is approaching my A value for f of x is equal to L. Yep. Good? And any questions, or it's pretty straightforward so far? Okay, so then that's looking at it graphically. And anything that I give you, you can graph it, but we're also probably more often going to be looking at how to work through this algebraically. So here's the first one. The limit as x approaches 2 for 3x squared minus x minus 5. I might as well throw in some review. What kind of function is this? Like if we were to graph it out, the 3x squared minus x minus 5, what is that? That's a parabola, right? So we're analyzing the equations in order to be able to tell that. The fact that it's a 3x squared, 2 is the highest degree, is what indicates it's a parabola. Okay, so there's some good review to build in, and you're gonna start to see what I mean, that this is easier, I would say, than all the other stuff you've done before at this point, because all we do to figure out although we are finding the limit as x approaches 2, that means that we can simply plug in that 2. So 3 times 2 squared minus 2 minus 5. So I'm just taking this value that I have here, and I'm simply plugging that in wherever I had an x in my equation. That stuff we've been doing for years. So we can see when we work our way through this, we would end up with a value of 5. Pretty straightforward. You see what I mean by it's just a bunch of old stuff we've done before, but there's new vocabulary, new way of looking at it. So the limit as x approaches 2, blah, 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 this is all just equal to 5 after working our way through that. Do you get, like, without us having to actually graph it out, does this make sense, the reason we're able to plug in that value? Yeah, so we're not finding the exact answer at that point, but by plugging it in how we would if we were looking for the answer at that point, it is telling us where it's approaching on the graph. Make sense? So that's pretty much the idea behind it. Let's take a look at some different scenarios of how this might show up, because after learning about that, the only other thing that happens is we change up the functions that we're working with. So we started with a parabola. Again, let me build in a little bit of review. So if I'm looking for the limit as x approaches 2 for x squared minus 4 over x minus 2. And then you get to see why those courses are called pre-calculus and why you practice all those things all these years. What kind of function is this one? What do we call this? And I'm going to continue to do this. You don't really need to know, but just building in review to refresh your memory. I heard someone whispering it. Is it Jeffrey? Or rational. Good? And then already looking at it, if I just plug in 2, we have that same old problem we talked about last day. We don't want 0 at the bottom. What's the smartest thing for us to do with this that we probably always should do anyways? Yeah, we want to factor, right? So whenever possible, step number 1 is simplify using all the tools and skills you've learned over the years. So for this, we can take this and factor it out to say I would get x, it's a difference of squares at the top, so x plus 2, x minus 2, and at the bottom we also have x minus 2, and I'm too lazy to keep writing out limit. I'm just going to do that. That's and then the whole reason we did this is that nicely cancels out top to bottom, so now I will actually write it out. We do have the limit as x approaches 2, and we have something much easier to work with. We have x plus 2. That's all that's left. So I can basically, if this is approaching 2, I can just put a 2 in there. So our value for all of this would just be, well, let me write it properly. It's equal to 4, but the best way, the limit as x approaches 2 for our function f of x is equal to 4. Pretty good? Okay. So let's sort of summarize this, or let me repeat this. The limit must be the same from both sides. I'm kind of just repeating what I already told you, but this is super important. That's the stuff, the nitpicky stuff that gets some people if you forget, because we're going to be picking up other things that we're going to be working on. So here's a good way for us to write this. and you'll see this written often, the limit as x approaches a, this notation is probably new to you. You might have done a bit of it last year in Pre-Calc 12, I'm not sure. So I'll go through it with you anyhow. So what this is saying is, the limit as x is approaching a from the negative side or from the left. That's what that little minus sign above is talking about. If that is equal to some value L, then it must also be equal to the limit as x approaches a, and then with that little plus sign at the top, that is referring to it approaching from the right side or from the positive values. Make sense? So again, not really a difficult concept, just a new way of looking at things, new notation. So I'm just going through slowly to set up the groundwork so you know what all this stuff means when you see it written down. And then this stuff is important, so let's put it in a nice big box. And I probably should have done that the same, but there you go. So that's an important concept that you need to know. I think it's important or helpful for you to have this in your notes as well. You can have a hole at the point of interest but still have a limit. So that too is just me repeating what I already told you earlier. Good? Questions or? Good. Let's look at yet another one. To practice this, so evaluate this. The limit as x approaches 0 for the absolute value of x over x. We're going to go through this together. I'm picking one of each of some odd or unusual circumstances so that we can sort of start to look at how this might show up. Here's an example of one, because you do know about absolute value functions, but this isn't like the previous one. Like you can't really factor things out here. It's a little more complicated, right? And we do see that the issue or the problem, similar to what we talked about last day, is that it says x approaches 0 at the bottom, and there's an x at the bottom, and we can't have that. So we kind of already know where this is headed, but I want to make sure that you clearly get this and are able to understand this. So here's a strategy that we usually avoid because at this point, we're so beyond table of values, but it's a tool, again, another thing that we've picked up or practiced over the years to help us to make sense of things. So use it if it's helpful. But we can see that at a value of 0, I'm just going to put a line here, or I guess I could say like undefined. We know that that can't happen or that won't exist or it's not possible, right? So usually, and again, this is sort of me building in review, what happens on a graph if we have that situation? So how does that show up on a graph if we were to graph this out? Yeah. You would get an asymptote. Everybody remember that? So maybe just again, because we're reviewing, it's been a while, we know that that would show up as an asymptote. And what usually happens around asymptotes is that you have values that approach from one side and the other side, either in that direction or that direction. But you know that there's activity that happens closer and closer and closer to the asymptote. So a smart way for us to start to get a sense, especially when it's been a while since we've done this, probably for most of you, is to pick values that are really close to 0 on the left side and on the right side. So on the minus side and on the plus side. And I'm going to I know you all know how to do this, so I'll just tell them to you. Like, let's say we started with negative 0.1, for example. We would get negative 1 here. If we did negative 0.01, we would get negative 1 here. And let's say I did negative 0.001. So you see the pattern of what we're trying to do. Just getting values closer and closer and closer to 0 without approaching 0. And those would all be at minus 1. So the way I want you to look at this, or the way I want us to make sense of this and tie it in with what we just did, is at this part here, I would say that the limit, sorry, let me change that. The limit as x approaches 0 from the left side, or from the negative values, for f of x, or f of x being this root x, or I mean absolute value x over x, is equal to negative 1. Okay, so I'm going to do something similar on the other side. So I'll do exactly the same thing, but going the other way. So I'll start with closer to there, and then I'll go a little bit further away. 0.1. And then we know that this time when we do this, it's going to be plus 1, plus 1, and plus 1. So again, to show you this, how this shows up using our new fancy notation, is the limit as x approaches 0 from the positive side for f of x is equal to positive 1. Usually when it's plus 1, we don't write it, so I'm not going to bother. But what we see is that when we make this comparison, this versus this, they are not the same. When they are not the same, so I'm going to say therefore, that's my little symbol for therefore, the limit as x approaches 0 for absolute value of x over x does not exist. If I'm lazy, I can let you be lazy. If you want to write DNE instead of writing out does not exist, that's totally fine. I know what it means. That's acceptable. But you can see the reason for that is because they're not the same. So you might get a question that, kind of like this one, is pretty obvious when you look at it. But part of this is, like math is about the answer, but it's also about the proof and the reason for it. So you need to understand where it's coming from and be able to explain or show or demonstrate, and this is a method that we could use to demonstrate that. So far so good? Questions about anything? Abteen? Sorry, say that again? We're not quite there yet, but yeah, eventually. Yeah. Good? Okay, and I didn't ask for this, but if we did want to, just really quickly, do you see that it would look like this? We would have this going on at one point, and then this going on at the other point, where that's 1 and that's negative 1. So this is basically to tie in. We did the table of values, we looked at the work behind it, and if you were to visually look at a graph, because you might get questions where you're just given this graph and asked about the limit that way, that's how this would show up or appear. So it's, if you look at it, if we're looking at the x value of 0 here, you can see that there's 2 different y values that it's approaching. So that's the first time we're seeing where it doesn't meet at the same place. Questions? Yeah?
Instead of approaching 0, if I say approaching like 2 or 3, would I still have
Oh, good question. So if on this same graph, let's say we picked some point over here, let's call it 3. Now, what's the answer if we ask for the limit as x approaches 3? It would be 1, because if we look at that point of interest, you see from both sides, it is approaching 3. But you guys are, it's good that you're thinking these things. You're getting a little bit ahead of where we're at. We are going to look at that. I think it's coming up next day. We're going to look at one-sided limits and getting into the nitty-gritty details, and that'll help to clear that up a bit, Jeffrey. But yes, so it does have a limit at 3. At 3, the limit would be 1, because from both sides at that point, it would be approaching the same value. Good? Other questions? Okay, so your work is page 18, numbers 1 to 2, 4BD, 5ABC, it's a complicated one, and 6. And then you're also doing page 212, numbers 1, 2A to F, and that's your work for today.